warahmatullahi wabarakatuh, and hi everyone. Today we are going to proceed to lesson 7, chapter 5. The topic is electromagnetic induction. Okay, so we need to cover 5.1a, 5.1b, 5.2a and 5.2c. 5.1 is magnetic flux. You need to know the definition and use the equation and use the formula for magnetic flux linkage. And for subtopic 5.2, induced EMF, you need to explain induced EMF by using Faraday's experiment, state and use Faraday's law, state and use Lenz's law, and derive these three equations. Definition of magnetic flux. Magnetic flux is defined as the scalar product between magnetic flux density, the symbol is B, and vector area, the symbol is A. Or the equation is phi equal to B dot A, because it's a scalar product, so B dot A, and we know that for scalar product cos theta, so in mathematically phi is equals to BA cos theta. Okay, phi is magnetic flux. Okay, and theta is the angle between the direction of B and A. Okay, for example, the green is the magnetic field B, and A is the vector of the area. Okay, this is the area. The circle is the area, and vector area is always normal to the area. Okay, so theta is the angle between the normal area and B. This is theta. Okay, B is magnitude of magnetic flux density, and A is area of the coil. Magnetic flux is a scalar quantity, so no direction. The unit is Weber or Tesla meter squared. Okay, how we can got the unit? Okay, phi is equals to BA. The unit for B is Tesla. The unit for A is meter squared. So the unit for phi is Tesla meter squared, TM squared. Next, what is magnetic flux linkage? The symbol for magnetic flux linkage is phi. This is also phi, and this is also phi. This symbol is for magnetic flux linkage, where the formula is N phi. Okay, this phi is for magnetic flux. Is N is equals to number of turns. Number of turns. Okay, N is number of turns. Phi is for 1 turn. Okay, if it has more than 1 turn, so the name is magnetic flux linkage, where we need to multiply with number of turns. Okay, phi is maximum when theta equals to 0. Okay, look at this diagram. The blue is B, the direction of magnetic field. Okay, this is the area. When the object is perpendicular to the magnetic field, the vector area and the magnetic field is parallel, so theta is equal to 0. Okay, why we state that it's maximum? Okay, because the magnetic field pass through the area is 4 lines. Okay, this is maximum. But when theta is equals to 90 degree, means the area and the magnetic field are perpendicular, are parallel. The vector area and B is perpendicular. So phi is 0 because no magnetic field pass through the area. Okay, note direction of vector A always perpendicular or normal to the surface area. Okay, as I stated before, and the magnetic flux is proportional to the number of field lines passed through the area. Okay, next we proceed to subtopic 5.2, induced EMF. Okay, for this subtopic, you need to explain induced EMF by using Faraday's experiment. From the experiment, when the position of the magnet is at rest, no deflection in the galvanometer. And when the magnet moves towards the coil, the deflection in one direction. Okay, when it moves to the coil, it will deflect in one direction. But if the magnet is at rest, so no deflection. And when the magnet moves away from the coil, the galvanometer will deflect to the opposite direction. Okay, and when the magnet is held stationary at the same position, no deflection in the galvanometer. Okay, now let we see the simulation if the magnet move toward rest and move away from the coil. When the bar magnet is at rest, no deflection in the voltmeter. When the bar magnet move towards the galvanometer, move towards the coil, we look at the voltmeter, it will deflect in one direction. And if at rest, no deflection on the voltmeter. When it's move away, the voltmeter will deflect to the opposite direction. And if at rest, again the voltmeter, no deflection. From the experiment, we can conclude that whenever there is relative motion between a conductor coil and a magnetic field, the flux linkage will changes, and the change in the flux will induce a voltage across a coil, and we call it as EMF induced. How we can increase the EMF induced in a coil? First, by increasing the number of turns in the coil. From the formula derived above, it is easily seen that if number of coil turns in a coil is increased, the induced EMF also get increased. Okay, now we have two coils. First coil is with 2 turns. The second coil with 4 turns. Okay, now the bar magnet is moved towards the coil with 2 turns, the voltmeter will deflect. But if the coil moves towards the coil with 4 turns, the deflection of the voltmeter is larger. Means that by increasing number of turns, the induced EMF will be increased. Next, we can increase the induced EMF in a coil by increasing the magnetic field strength B. Okay, if B surrounding the coil is increased, the magnetic flux is increased, and the induced EMF will be increased. Theoretically, if the coil passes through a stronger magnetic field, there will be more lines of force for the coil to cut in. Hence, there will be more EMF induced. We can increase the number of magnetic field lines by move towards the magnet bar to the coil. Okay, so the voltmeter will deflect larger. Means B is increased when we move towards the bar magnet to the coil, and the induced EMF will be larger or increased. We can increase the EMF induced by increasing the speed of the relative motion between the coil and the magnet. If the speed between the coil and bar magnet is increased from the previous value, so the coil will cut the line's flux at a faster rate. So more induced EMF will be produced. Subtopic, you need to state and use Faraday's law. Okay, Faraday's law states that the magnitude of the induced EMF is proportional to the rate change of the magnetic flux. Rate change is d over dt. Magnetic flux is 5. So, mathematically, induced EMF is directly proportional to negative d phi over dt. Or the equation is EMF is equal to negative d phi over dt. d phi is change of magnetic flux. dt is change of time. And EMF is induced EMF. Okay, the negative sign indicates the direction of the induced EMF always opposed to change of magnetic flux producing it, and it's known as Lenz's law. Let's proceed to the next learning outcome. Derive and use induced EMF in straight conductor, in a coil, and in a rotating coil. Okay, first let's derive the induced EMF for straight conductor. Okay, let's say we have a conductor PQ is placed in a uniform magnetic field. Okay, the blue cross is the direction of magnetic field into the paper. Okay, and the conductor is moving to the right. Okay, so magnetic field is experienced directed downward, acts on the electrons in the conductor. Because of the magnetic force, the free electrons move to the lower end and accumulate there, leaving the positive charge at the upper end. Okay, because of this separation, positive and negative, an electric field is produced, where electric field is upward. Fe is upward. The charge stops flowing when the downward magnetic force is balanced by the upward electric force. Okay, because the charge, because of the force is balanced, so the electron is at equilibrium. In equilibrium, Fe, electric field, is equal to Fb, magnetic field. We know that the formula for Fe is QE and Fb is BQV sin theta. So we can cancel Q. So E is equals to BV sin theta. And from equation, V equals to ED and EMF equals to EL. And the formula is EMF equals to BV sin theta. So we can get the equation EMF for a straight conductor is EMF equals to BLV sin theta. Okay, this is equation for straight conductor, induced EMF for straight conductor, and it's also called motional EMF field. In the coil which causes induced EMF, we know that induced EMF is equals to d phi over dt, and phi is equals to BA cos theta. So, how we can change the value of phi? By moving a magnet towards or away from the coil. When moved towards or away the magnet through a coil, the B will increase or decrease. Okay, by moving the coil in or out of the magnetic field. Okay, just now we move the magnet bar. Okay, but now we move the coil towards or away, so B will increase or decrease. Next, we can change the area because phi is depends on area. So when we change the area, the phi also change, so it will be induced EMF. the last one, by rotating the coil relative to the magnet. Okay, when we rotate the coil, the theta will change. Either it's increase or decrease, because the formula is phi equals to BA cos theta. So when theta change, phi also change, and it will induce EMF. Equation, phi is equals to BA cos theta. When theta is equal to 0, phi is equals to BA. Okay, equation of EMF induced in a coil. Okay, if the phi is changed, phi final minus phi initial. If the B is changed, so B final minus B initial at constant area. If the area is changed, A final minus A initial, and the magnetic field is constant. So the induced current in the coil, the formula is phi is equals to negative N d phi over dt, where N is number of turns, and EMF is equals to IR, resistance of the coil. Okay, so the formula is IR equals to N phi and d phi over dt. To calculate the magnitude of the induced EMF, the negative sign can be ignored because you just calculate the magnitude. No need to determine the direction. Next, we will discuss the derivation for induced EMF in a rotating coil. Okay, consider a rectangular coil of n turns. Okay, this is a rectangular coil with n turns, and each area is A, being rotated mechanically with constant angular velocity. Okay, omega is the angular velocity, and it placed in a uniform magnetic field. Okay, the blue line is uniform magnetic field. The symbol is B. About n axis is shown in figure below. Okay, when the vector area, as we discussed before, it's always normal to the area of the coil. Okay, vector area A is at angle theta to the magnetic field B. The magnetic flux is given by this equation. Okay, we have discussed this equation before. Okay, and we know that theta is equals to omega t, and omega is equals to 2 pi t equals to 2 pi over period. Okay, and so phi is equals to BA cos theta, because BA cos omega t, because theta is equals to omega t. Okay, from Faraday's law, we know that induced EMF equals to negative N d phi over dt. So phi is equals to BA cos omega t. Okay, we substitute, this is negative NBA d cos omega t over dt, because N, B, and A are constant. No need to differentiate N, B, and A because they are constant. Okay, the only change is the time. So we need to differentiate cos omega t. We know that differentiate omega t, we will get negative sin omega t. So substitute, this is negative, so we will get the equation NBA omega sin omega t. So the formula for induced EMF in a rotating coil is EMF equals to NBA omega sin omega t. Okay, for maximum EMF, Emax or E naught, the formula is NBA omega, when sin theta is maximum is equals to 1. The conclusion, the EMF in a rotating coil is sinusoidal alternating EMF as shown in graph EMF against T. Okay, from formula EMF equals to NBA omega sin theta. Okay, if the coil is perpendicular to the magnetic field, the A and B are parallel, so theta is equal to 0. We use formula EMF equals to NBA omega sin theta. Theta is 0, so EMF is equals to 0. So This is the point. EMF is 0. Okay, next. When at this position, when the coil and the magnetic field are parallel, A and B are perpendicular. Theta equals to 90. So when theta equals to 90, we still applying the same formula. NBA omega sine 90 degree. We know that sine 90 is 1. So EMF is maximum. NBA omega. That's why it's at maximum point when at this position. Okay, and so on. As we proceed to the next subtopic, Lenz's law. The learning outcome is state and use Lenz's law to determine the direction of induced current. Okay, Faraday's law state about the magnitude, but the Lenz's law will state about the direction. Okay, Lenz's law states that an induced electric current always flows in such a direction that opposes the change producing it. For example, a bar magnet moves towards a solenoid. Okay, we know that the magnetic field from the North Pole is outward. So when the bar magnet moves towards the solenoid, the magnetic field lines across the solenoid will increase. But Lenz's law states that it always opposes the changes. So there will have be induced to decrease the magnetic field lines through the solenoid. So the magnetic field lines, the B induced will always opposite direction to the magnet bar. So you can determine the induced current by using right hand grip rule, where your thumb finger is for B induced and your curved finger is for induced current. So now we know that induced current is downward, and across the galvanometer it will deflect to the right. Next example, the same bar magnet move away from the solenoid. Okay, when it move away from the solenoid, the magnetic field across the solenoid will decrease, but Lenz's law always opposes the changes. So B induced is opposite. Okay, B induced want to remain the magnetic field across the solenoid, so it will increasing the magnetic field across the solenoid. So B induced is same direction. Okay, then it will increase the it will increase the magnetic field across the solenoid. So we still use right hand grip rule. Your thumb finger is for B induced and your curved finger is for induced current will be upright. This is current induced. So across the galvanometer, it will deflect to the left. I have discussed all these 4 subtopic for lesson 7. So thank you.